In the previous video, we proved all of the derivatives for the trigonometric functions, and in this video we will prove all of the derivatives for the inverse trigonometric functions. What we will be needing for each of these proofs is the following rule for computing the derivative of a function's inverse. If I have a function f with an inverse f to the negative 1 and a derivative f prime, then I can compute f to the negative 1 prime. That is, I can compute the derivative of the inverse function. Now if you look closely at this formula, you'll see one problem, and that is if I end up with a 0 here, because we cannot divide by 0, the derivative will not be defined at that point. So let's see what that would look like. If I had a function, let's just say I had a function like this, and I draw its inverse, so in other words, I draw its reflection about the line f of x equals x, and I end up with something like this, right? Then if our function has a point at which its derivative is 0, the inverse will have a non-defined derivative at its corresponding point. And that is what happens when we have a 0 in the denominator here. The other thing that we'll be needing will be the Pythagorean trigonometric identities. Sine squared of x plus cosine squared of x is equal to 1, and a couple of different versions of those. For example, if I divide both sides of this equation by cosine squared of x, I end up with this equation. And if I divide both of the sides of this equation with sine squared of x, then I end up with this equation. So these are just different versions of the Pythagorean trigonometric identity. So let's get started with arcsine. First of all, let x be in the open interval between negative 1 and 1. Now this is the first problem that we're going to encounter in this proof. Why didn't we say let x be in the closed interval between negative 1 and 1? After all, that's the actual domain for arcsine, right? And the reason is what we talked about before, is that a function sometimes might have a point where its derivative is not defined. So let's take a look at the graph for sine. Then where sine is equal to 1, the slope is 0. And where sine is equal to negative 1, the slope is also 0. So the derivative is not defined at those points. Okay, but now we can get on with the computations for the derivative for arc sine of x. First thing we can do is use our formula here, and we get this. In other words, f is here just sine, and so we're taking f prime, so sine prime of, and then f to the negative 1, that's the inverse, and that's what we're actually talking about here, arc sine of x, right? So we've just subbed that in here, 1 over sine prime of arc sine of x. But we do know what the derivative of sine is. We know that that's cosine, so we can go ahead and sub that in as well. And at this point we could say we're through. That is the answer. The derivative of arc sine of x is just 1 over cosine of arc sine of x. But if we want to know the answer in terms of x and not just in terms of arc sine of x, we can continue. Our problem here is that we have this cosine of arc sine of x, right? If we had something like sine of arc sine of x, then things would cancel and we could maybe make some progress. So could we somehow replace this cosine with a sine? Well, if we use this equation here, maybe we could. We could just solve for cosine squared of x and put that sine squared of x over on the other side and then just sub in. The problem is, in order to do that, we would somehow have to get a cosine squared, which means we would also have to then take the square root of that, since we can't just change the denominator. Can we do that? Well, let's say that cosine of arc sine of x is negative 2/3, for example. Now, if I square that and then take the square root of it, since the square root function always gives me a positive value, then I end up with, okay, so negative 2/3 squared is 4/9, and then take the square root of 4/9, and I end up with 2/3, which is not equal, of course, to negative 2/3. So this is not going to be a step that I can take in general. I have to justify why I can do that. So let's look at arc sine of x. arc sine of x is going to spit out some value between negative pi over 2 and pi over 2. Right? That is the range for arc sine of x. Negative pi over 2 to pi over 2. Now let's see what cosine is then going to do with some value between negative pi over 2 and pi over 2. So here's the graph for cosine. Here's negative pi over 2 and here's pi over 2. And we see that cosine is going to then give us some non-negative value, and that makes it legal to do what we wanted to do. In other words, since the denominator here is some non-negative value, if we square it and then take the square root of it, we get the same thing. In other words, this step was legal. At this point, we can now use our Pythagorean trigonometric identity, as we mentioned before, and sub in here 1 minus sine squared of x, which is exactly what we do here. And sine of arcsine of x is obviously equal to x, and that gives us our final answer, 1 over the square root of 1 minus x squared. So now let's move on to the next proof, but let's skip over arc secant for now because that's a bit of a difficult case. Let's move on to arctangent, which is quite simple. So we start out with some real number x. It turns out there is this time no point at which there's not a derivative. And we start out again by just subbing in to the formula that we had above and end up with tangent prime of arctangent of x. And since we do know the derivative of tangent, it's just secant squared, we can sub that in as well. And at this point, we have secant squared of something, which means we can look at this here, secant squared of something. We can just sub in here, in other words, tangent squared of x plus 1, which is exactly what we do. We have here then 1 plus tangent squared of arctangent of x, and since tangent of arctangent of x is just x, we end up with 1 over 1 plus x squared, and we're done with arctangent. Now we turn our attention to arc secant, and that is an interesting case. So we want x to be somewhere in the, basically in the domain for arc secant, but not quite. Since here again we have open intervals on these sides, we're having to exclude the negative 1 and the 1, and we can see why that is. Here's the graph for secant, because when secant is equal to 1, the slope is equal to 0, and when secant is equal to negative 1, the slope is also equal to 0. So we just have to exclude those. The derivative is not defined there. But other than that, we can proceed. Let's start just by doing the computations and seeing where we get into trouble. So we want to know the derivative of arc secant of x. We sub into our formula. We know the derivative of secant. It's just secant of x tangent of x, right? So we just sub that in here as well. And we also know what secant of arc secant of x is, right? That's just x. So we can simplify this far. It's at this point that we get a problem again. Somehow we want to get rid of this weird looking expression, tangent of arc secant of x. So we want to do our trick again, where we square an expression and then take the square root of it. So let's see if we can do that here. Arc secant of x is going to be either between pi over 2 and pi, or 0 and pi over 2. So we're going to have to now know what x is equal to. So let's say that we're dealing first with some negative x. Okay, so x is some negative value. So in other words, x is some value here. So arc secant is going to spit out some value on the open interval between pi over 2 and pi. And now we need to see what tangent is going to do with that. Something between pi over 2 and pi. So between pi over 2 and pi. And we see that we end up with a negative value, since we also can't get 0 since we're dealing with an open interval. So what can we do with that? Well, we know now that we can't just square that and take the square root, as we saw with our example of negative 2/3. That won't work. So how do we proceed? And this is the first real problem that you get in this proof. What we can do is, instead of just looking at this tangent here, which is actually our problem, we can look at the entire denominator. Since x itself is negative, and since this value that we're getting out of tangent here is also negative, the entire denominator is positive. So we can square that and take the square root of it, which is exactly what we do here. So we would have liked, perhaps, just to square this tangent expression and then take the square root of that, but that wouldn't work. So we had to do it with the entire denominator. And at this point, we can break this up into two different radicals. So we have the square root of x squared, and since we now have a tangent squared, we can use these trigonometric identities here. We have the tangent squared here. So if we solve for tangent squared, that gives us secant squared of x minus 1, and we can sub that in there. And all we have to do now, we're one step from the end, is just to figure out what each of these radicals gives us. So the square root of x squared, one might think, oh well, that's just x, but you have to watch out again, because if x is a negative number, again something like negative 2/3, then if you square it and then take the square root, it gives you a different value. So we're going to have to make sure that that root that we get there is positive. In other words, we have to say it is the absolute value of x. And this here allows itself to be simplified rather easily, since secant of arcsecant of x is just equal to x. So we end up with the square root of x squared minus 1. And that is the answer that we wanted to get. Now at this point, there's something else interesting about arcsecant, and that is that sometimes the derivative is given as being 1 over x times the square root of x squared minus 1. So in other words, the absolute value is left off. Now why would that be? That has to do with the range that has been agreed upon for arcsecant. You see here that the range for arcsecant is always giving us some value either between 0 and pi over 2, in case x is a positive number, or between pi over 2 and pi if x is a negative number. But this range is not universally agreed upon. There are those who use different ranges here, and that actually leads to different derivatives. Let's take a closer look at the graph for secant to see what I mean by that. And actually, let's say that it's up to us to decide what the output range of arcsecant should be. And let's say we're thinking of some specific value, let's say the value 2, and we want to know what we would have to take the secant of in order to get 2. Well, what answer should we give? We could give this answer here. That gives us 2. Or we could give this answer here. The secant of that also gives us 2. Or we could move way over on the right and imagine how this curve continues there and also take the secant of that value. That would also give us 2. And it turns out that for positive values, like we're dealing with here with 2, most people agree that secant should give you a value between 0 and pi over 2. So in other words, we're using this part of the curve here. But what if someone says, I want to know what I have to take the secant of to get a negative 2? Well, again, I could maybe take this point here. That looks like that's about negative 2. Or I could take maybe this point here. That's also going to negative 2. Or I could take this point here or this point here. So which one of these do I want to take? Well, what we did was to use this portion of the curve down here with the positive slope, just like the other portion of the curve that we used had a positive slope, and gives a value between pi over 2 and pi. Others use this part of the curve here that has a negative slope, as you can see, and gives a value between pi and 3 pi over 2. Yet others use a different portion of the graph altogether, this part right here that also has a negative slope and gives a value between negative pi and negative pi over 2. And these differences account for the differences in the way the derivatives look. Our derivatives were always positive, and our curves always had positive slope. Now, these other versions that one can do have a negative slope exactly then when x is negative, which accounts for the absence of the absolute value sign here. Okay, so those are the first three derivatives we wanted to do: arcsine, arcsecant, and arctangent. Now the next three will be very easy because we can use these three to derive them. And what we're going to make use of is a certain identity involving cofunctions. So it turns out that the arccosine of x is equal to pi over 2 minus the arcsine of x. And arccosecant of x, for example, is equal to pi over 2 minus arcsecant of x. And so that we have a conception here of what's going on, let's rewrite that first equation in a slightly different way. Let's write arccosine of x plus arcsine of x just adds up to 90 degrees. In other words, pi over 2. So arccosine of x is, of course, just an angle. It's the angle you would have to take the cosine of in order to get x. And arcsine of x is also just an angle. It's the angle that you would have to take the sine of in order to get x. And since sine and cosine are cofunctions, and the co stands for complementary, these two angles are complementary and hence add up to pi over 2. And we can use this fact to make the next three proofs very short. So we want to take the derivative of arccosine of x. We just rewrite it as pi over 2 minus arcsine of x. We take the derivative of each term. This constant here just goes to 0, and we end up with a negative sign in front of the derivative for arcsine of x, which gives us our answer. So for the next two proofs that we want to do, the same thing will happen. We'll just end up with a negative sign in front of the inverse of the cofunction. So for arccosecant, we just do the same thing. We rewrite it in terms of arcsecant. This derivative goes to 0. We end up with a negative sign in front of the derivative for arcsecant, and we have our answer. The same goes for arccotangent. We rewrite, the derivative is 0. We have a negative sign, and that gives us our answer. And with that, we have proved all of the derivatives for the inverse trigonometric functions, that is, those at the bottom of our list. And since in the previous video we proved all of them at the top of our list, we have now proved all of the derivatives in our list.